Rahim. This is our second recorded lecture that's supposed to be on 18th of March, the last Wednesday. This lecture we start studying chapter 4, continuous random variables and their properties. The outline of this chapter will go as follows. We'll start by defining the continuous random variables and then go to studying the probability density function as a tool to compute the probabilities that relate to this type of variables, and then use the cumulative distribution function to compute the cumulative probabilities, and then we'll go to discuss concepts of expectation, variance, moment, and the moment genetic function. As we see here, most of the concepts that we are studying here are already have been studied in the case of the discrete case, but we'll see that we'll manipulate this concept in a different way using the continuous random variables. We'll start first by defining the continuous random variables. Before we study the continuous random variable, I prefer to remember the discrete random variable. In the discrete random variable, we say that we can have a variable that may take finite possible values or infinite or but countable possible values. For example, if for the case of finite possible values, if we have an experiment of tossing one die, we will the number that show up will be 1, 2, 3, 4, 5, or 6. Another random variable, which is the number of kids in a family. This could be 1, 2, 3, 4, 5, 6, 7, up to 8. All these examples of a random variable that take finite separate values. The random variable may also take values but infinite but countable. What we mean by infinite? Infinite that we can have an upper limit to these possible values. For example, if we are discussing the number of accidents that occur on a highway in a country, and you are measuring this number on a period of month, okay? So we can, for example, have 1 accident, 2 accidents, 3, or maybe 500 accidents. So we don't have an upper limit for this kind of variable. We discussed this kind of variable is that we have to relate the variable to a random experiment with a sample space, and then we'll define the possible outcome of a random variable on this sample space to compute the probability that assigned to each value. The function that make this link between the values and the probability we studied here as p of y. If we call the variable as y, this is the probability mass function that have to be summed to 1 all over the possible values of y. That was the case of the discrete random variables. Now move to the continuous random variables. Let's start by introducing a definition. The random variable is said to be continuous when it takes on any value in an interval. So the continuous random variables doesn't take a distinct or separate values such as the discrete random variable. Here we're defining the values over interval. The continuous random variable, another definition, is defined when the sample space can take an uncountably infinite number of sample events. So the sample space that relates to the continuous random variables are itself take an uncountable infinite number of values. The sample space for the continuous random variable can be defined on the whole real line R or a segment, which means a part of R. To make the idea of the continuous random variable more clear, let's discuss some examples. Here we have 2 examples. The first is the daily rainfall. The daily rainfall at a specified geographical point with measuring equipment of perfect accuracy. So I wanted to take your attention by the word measuring here. In fact, what's make the difference, or the key difference between the discrete and the continuous random variable is we can take values of the continuous random variable by measuring. Okay, in most cases we need a measuring tool to take the values, because the values, as we can see, is defined on an interval, so we need to find the exact number. But in the case of the discrete, we're just counting the values. So this is the main difference between the continuous and the discrete random variables. So here in the example, the amount of daily rainfall could take on any value between 0 and 5 inch. We are measuring the rainfall on a daily basis. These values could be any value between 0 and 5 inches. As a result, each of the uncountably infinite number of points in the interval 0 and 5 represent a distinct possible value of the amount of a rainfall in a day. Fine. The next example is the waiting time of a customer spent in a line in the store. At the store, the waiting time could take any positive real valued number. We might talk about the event that a customer wait between 5 and 10 minutes, and not about the event that the customer wait exactly 5 and a quarter minutes. As you can see here for these examples, the value that can be defined, the random variable, are measuring but over the interval. Now move to how can we compute the probability of these infinite possible values for the continuous random variable, or how can we define the probability? The probability distribution for a discrete random variable can always be given by assigning a non-negative probability to each of the possible values, such that the sum of all possibilities or all probabilities must be equal to 1. That we just mentioned about the discrete random variable. Unfortunately, the probability distribution for a continuous random variable cannot be specified in the same way, because here we can never make an assigning between a probability and a certain value, because we don't have a certain value. We have an infinite range of values over an interval. So this can never be done as we can do in the case of the discrete random variable. It is mathematically impossible to assign non-zero probabilities to all the points of a line interval while satisfying the requirement that the probabilities of distinct possible values sum to 1. So this is, as we can see, is very impossible in the case of the continuous random variable. Now move to how can we find a technique to compute the probability that relate to these type of variables. So we'll discuss the probability density function. In fact, this concept is corresponding to the probability mass function in case of the discrete random variable. Let's try to make it clear. We'll start with discussing an example. If we measuring a depth of a water in a certain well, we know that the depth of a water well is changing every day, or changing every hour. This relates to many factors: the rainfall, the sun temperature, maybe the season, maybe the consuming of the water in the well by people. So many factors that make the depth of the well, the water in the well, may be changing from an hour to an hour, from a day to a day. So this is a variable. Clear? Let's imagine the case when we are measuring the depth of the water in the well for 5 successive days. Using the measuring tool, we have here 5 different numbers, and you can see the difference are the 5 numbers for different 5 days are completely different, because we are measuring the exact number. So here we are measuring the exact number, or the exact amount of depth, the exact number. Okay, as you can see, 30.115, 30.1454, and so on. If we try to make a rounding to these numbers, the first trial is if we try to make rounding to the nearest one. What we mean by the nearest one, I mean to round it to a whole number, to a whole integer. So according to the rounding way, the first value will be 30, the second value will be 30, the third 30, 30, 30. All the possible values on different 5 days represent just one value, which is 30. Fine. If we try to make another rounding, let's, for example, to make rounding to the 10th value. What we mean by the 10th? Rounding to the first digit after the decimal point, or the decimal symbol. So the first value will be approximated to 30.1. The second one will be 30.2. The third will be 29.6, 29.8, and 30.1. According to this rounding technique, we have how many different or how many distinct values? We have here 3.1 and 3.1. We just have two repeated value, and the other three values are completely different. So at the end, we have how many values? We have 4 different values. We have 4 different values. Now, try to make another rounding technique. Let's, for example, make the round to the nearest 100. The nearest 100 means make the round to the second place or the second digit after the decimal point. So the first will be rounding to 30.12. The second will be 30.15. The third will be 29.56. And then 29.79 and 30.13. As you can see here, there is no two similar points. So we have 5 different ways for the 5 different days that which we need to approximate to the idea. How when we make the rounding more and more, okay, we'll have infinite values of the random variables. Okay, if we try to represent the first, if we try to represent the probability that assigned to each of those values for the 3 different ways of rounding. The first one, if we try to represent the probabilities, we can say, if for example, here we are talking about 5 days. What about if we are measuring the depth of the water well for 100 days? Okay, for 100 days, by this way of rounding, we can get a possible finite values. So we can represent this probability distribution by a probability histogram, a histogram probability, right? So this will be the case as here represented by the first graph, this one. Okay, so for we say for 100 days we have 1, 2, 3, 4, 5, 6, 7 different values by this way of rounding. But when we use the second way of rounding, okay, so we are dividing each interval here to more simpler or more higher intervals. So the histogram will be like this one. According to the third rounding technique, we'll find that it's impossible to represent each value in this range for the random variable. So we find that the histogram will move to a curve like this. Okay, now let's move to read again to the slides of the concept. If we round the depth of water to the nearest meter or centimeter, we will be dealing with a discrete random variable. That is the first case. When we are rounding to the nearest whole number, whose probability distribution may be pictured by a histogram. That was the first case. If we keep rounding the depth to a smaller unit of measurement, the probability histogram of the probability distribution of the corresponding discrete random variables will approach the continuous curve, and the sum of the areas of the rectangles is the area under the curve, which is supposed to equal to 1. So, as you can see here, in the first case, which is very similar to the discrete one, we say that the area under this rectangle, have to be sum to 1. The case the same for these rectangles here in the second histogram. So the area will be generalized for the case of the curve to be the area under this, which is shaded here in red, this area have to be 1. This area have to be computed, we call it total area. This total area have to be summed to 1. Fine. The curve is the probability density function of x. This curve we call it the probability density function. It can be developed for the previous example as follows. So A represents the probability histogram of the depth measured to the nearest meter. The B represented the probability of the probability histogram of depth measured to the nearest centimeter. And number C is the limit of the sequence of the discrete histogram. Fine. So, as we can see here, it's impossible in the third case, it is impossible that we assign a probability to a certain value on the real line. Okay? We can, if we try to discuss the way in another way, you remember when we are, let's move to the example that we write here. Okay, if we say, for example, we have 50 days. We are measuring here. We are measuring here the depth of the water for 50 days. Okay, if we try to find the probability if we try to find the probability that y equals 30. According to the definition of probability, this may be done by counting the number of 30 we have in the whole 50 days. And here we have 1, 2, 3, 4, 5 divided by the whole sample space, which is 50 days. Fine? Okay. If we try now to find the value of, if we try here to find, for example, the value of, say, for example, 29.6, okay, and we're measuring these for, say, for example, 100 days. The value will be 1 divided 100. Okay, now move to the third one. If we try to measuring by this way, the value all over, say, for example, 500 days. So each of one of them will be represented by 1 divided by 500. Okay, so in each of those, we are dividing to a smaller intervals. Okay, so to find the probability that assigned to a value will be 0. Why it's 0? Because the denominator will be very high number. So if we imagine that all the time the value will be, the numerator will be 1, because we didn't have more than 1. Okay, by this rounding we don't have two different values. We have all the time the exact number are completely different all over the days we are measuring the depth of the water well. Okay, so when we divide by the total number of days of the sample space, this will be represented by a constant which is very few number divided by a number which is very high. So this probability have to be by this way tends to 0. That's why we are saying that the probability that the continuous random variable equal to a certain value, say A, probability that y equal a certain value, say A, equal to 0. This can never be done. If we imagine the case when we are drawing the probability density function, if we try to imagine that A is located here, and this is the value, this is y, this is the value of the random variable. So if we try to find this value as a area, okay, if we try to comparing between this case and another case, if we have the case, if we are measuring the possible values of y, the probability that y may take a values between two boundaries or two endpoints A and B. So this area will be represented by this shaded area. But here we just have one line. How can we measure an area over a line? We have a height, and we don't have base. Here we have a base, which is b minus a, right? And we have a height. Okay, so this area have value, but this area have to be 0. That's why probability of y equal a certain value, a certain or a specific value equal to 0. Fine? Continuous random variables probabilities are always associated with intervals. We always compute the probability over intervals. So probability that y take a certain or a specific value, this probability equal to 0 for any real number c. If this a particular value is denoted by c, and c is a real value number. This can be summarized as there are infinite set of possible values, so the probability that the variable take any particular value has to be 0. Okay? And now, how can we use the probability density function to compute the probability that related to the random variable, or the probability that the random variable take value within a range, or within a range between two endpoints? In fact, we use the area under the curve. The area under the curve of the p.d.f, and the p.d.f we denote by p.d.f is the probability density function. So p.d.f is the probability density function. So area under the curve of the p.d.f give probabilities associated with intervals. Precisely the area over a certain interval, if we have an interval, say for example, a and b. If we have an interval of a and b, how can we compute the probability that relates to a and b? This can be done by the finite integral of the p.d.f over this specified intervals. More precisely, this can be computed as, or mathematically, the probability that a random variable y lies within an interval a and b, denoted as the probability between brackets that y belongs to a closed interval a and b, where a and b are two real valued values. What we mean by real valued values, this means that a and b are both belongs to the set of real value number, such that, or provided that a is less than or equal b. So this is represented by graphically by this area here. So this is the random variable y. If we need to find the probability that y takes the value between a and b, this can be done mathematically by this equation. This be done by this equation, that probability that y takes the value between a and b equal to the finite integral of the p.d.f over this interval. So we are computing the integral between a and b, so this infinite integral is computed over the interval a and b, so the integral is read as integral from a and b for the p.d.f, and graphically this is represented by this shaded area in gray. Note that for continuous random variables, because we know that the probability that y take a certain value a is equal to 0, so these are equivalent probability. So if we want to compute probability that y take value between a and b, is the same as that y take values between a and b while a is inclusive, and equivalent also to the value of the probability that y takes the value between a and b b is inclusive, or equivalent to the probability that y take between a and b and both a and b are inclusive. So that's because the probability that y takes a certain value equal to 0, that make these statements are all equivalent, which is not true for the discrete random variables. Now move to the properties of the probability density function. Is there any properties? Yes, a function f can serve as a probability density function of a continuous random variable y if its value fy satisfy the following condition. We have two conditions, in fact. The first one, that this p.d.f have to be greater than 0. It can never be negative function. It is positive function. For any value y, and y may take any value between negative infinity to infinity, which means y belongs to the R, the set of the real number. So first, this function have to be positive, and the integral all over for all possible values of y from negative infinity to infinity for this p.d.f. have to be equal to 1. This is very similar to the discrete case when we are summing all over the probability mass function all over y to be 1. This is very similar to this condition. Okay, what about this condition? This condition means if we are graphing the f of y, if this is the xy plane, and here we have the whole possible of y from negative infinity to infinity. So fy to be positive, this means is represented in this part, which is the first quarter and fourth quarter, which is the part when f of y is greater than or equal to 0. Fine? Solving some examples. Here we have example number 1. We define a random variable y has the following p.d.f. The p.d.f f of y take the form c y to the power 2, and the support of this p.d.f is y take values between 0 and 2. The first question here, find the value of c that make the p.d.f f of y is a valid density function. What we mean by a valid density function? A valid density function means that it satisfies all the conditions of the probability mass function of the probability density function. The first condition, if you remember, was, here we have the example. The first condition was the integration of the p.d.f for all over the all values of y have to be 1. Here, negative infinity and infinity, in fact, negative infinity and infinity indicates for the lower limit in the support and the upper limit. Because we don't know the support of the function, so it is written theoretically as it takes the value from negative infinity to infinity. So if we try now to we need to find the value c that make this p.d.f, that make this condition come true. Okay, so here we'll substitute for the upper and the lower limit by the support here, which is from 0 to 2. For c y to the power 2 dy equal 1. So the equation will be, we have here c is a constant, we have here c is a constant, so c will brought out of the integration. So this will be y to the power 2 dy, and this have to be equal to 1. So this can be c, and the integration of y to the power 2, this is a power function, this will be y, and then the power will be added by 1 to 3, and then will be divided by the new power, which is 3, and then we'll substitute by the limits of the integral from 0 to 2. This have to be equal to 1, and then we'll substitute for y from 2 and 0, from 2 to 0. We'll substitute with the upper limit by 2, so we have here y to the power 3, which is 2 to the power 3, which is 8, divided 3, negative y to the power 3, 0 to the power 3, which is 0, equal 1. Then c times 8 divided by 3 equal to 1. Then c equal 3 divided 8. At the end, after we find the value of c, we need to substitute here in the probability density function by the value of a of c. then our function will be f of y equal 3 divided 8 y to the power 2, and y takes the value from 0 to 2. Now move to the next question. Find the probability that y take value from 1 to 2. We have another interval within, here we have f of y is defined only over from 0 to 2. This is the real number of y. So this function is defined here over this, only over this area, and we need to find the probability that y may take from 1 to 2. So we need to find this shaded area. Again, we find a probability that a random variable take values within an interval is computed as the finite integral of the p.d.f over this integral, over this interval. So this will be done to find the probability that y takes from 1 to 2. This will be done by integrating the function, the p.d.f over this integral. So we'll substitute by the p.d.f y to the power 2 dy. This will be 3 over 8 y to the power 3 divided 3, and then we'll substitute from 1 to 2. 3 will be eliminated by 3. This will have 1 over 8 here, and y to the power 3, which is 8, negative 1 to the power 3, which is 1. At the end, this will be 7 over 8. This is the value of the probability. The next question is find the probability that y take values from 1 to 2. In fact, we don't need to find this mathematically, because those intervals are equivalent. They are only different in the inclusion of the endpoints 1 and 2. Here 1 and 2 is inclusive, but here does not inclusive. And we know that probability y equal 1 is 0, and probability that y equal 2 is 0. So those probability have to be the same. So probability that y takes a value from 1 to 2 have to be 7 divided by 8. And this is the final answer. Now move to the next exercise. Here we need to find first c that makes this p.d.f or make this function is a p.d.f, and then compute this probability. Now move to find the c at first for this exercise. Here is the exercise. We need to find the c. Will follow the same way. The definition says that the integral all over the whole values of y from negative infinity to infinity for the p.d.f have to be 1. Then we'll substitute with the lower and upper limit with 0 and 1 according to the support of the function in the exercise. This will be cy to the power 3, 1 minus y dy. This has to be 1. And then this will be integral from 0 to 1, y to the power 3 will multiply y3 times 1 minus y. So this will be y to the power 3 minus y to the power 4 equal 1. This will be c y to the power 4 divided by the new power minus y to the power 5 divided by the new power. After we finish, we substitute with the limits from 0 to 1 and equal this to 1. This will be, when we substitute with 1, this will be 1/4 minus 1/5. And then when we substitute minus 0, all these terms will be 0. All of this equal to 1. This will be 20 here, and then will be 5 minus 4 equal 1. Then c divided 20 equal 1. So c equal 20. Now move to the next question. So c equal 20, that makes this function is a p.d.f. Now we need to find this probability that y is less than half. We know that y take values in the support on which the p.d.f is defined. Y take values from 0 to 1. If we need to find y less than or equal half, this means we need to find the probability that y take value from 0 to half. So this can be done again by finding the area under the p.d.f over this interval. Okay, so this can be done by as follow. The probability that y less than or equal half equal to the integral from over the interval from 0 to half. So this will be the integral from 0 to half for the p.d.f, which is 20 y to the power 3 1 minus y dy. This will be 20 y to the power 4 divided 4 minus y to the power 5 divided 5, and then substitute from 0 to half equal 20. And here we have 1 divided by 8 to the power 4. Half to the power 4 is 16. 16 times 4 minus half to the power 5, which is 32 times 5. All of this at the end, as we can see here, will be this probability can be computed as 3 divided 16. This will be 3 divided 16. Then we need to find the probability that y greater than or equal half. Okay. In fact, we don't need to find this by integrating the p.d.f over the interval from half to 1, because this is in fact the complement of this set. So this will be the complement of the probability that y is less than or equal half, because we have that y takes a value between 0 and 1. So if we have the probability, if this is the p.d.f, if we have the probability, and this is the value of y, if we have the probability that y takes the value less than or equal half, so this is the probability, this probability, which is denoted by cross here, can be done by, because we know that the area under this, the whole curve is 1. This area is 1. So this area can be done by 1 minus this area. Fine. So this will be 1 minus 3 divided 16, which is 13 divided 16. At the last example here, 13 divided 16. In the last example here, we have another formula of the p.d.f, which is c divided by square root of y, and y takes the value from 0 to 1, and we need to find c that makes this is a p.d.f. Again, I'm just repeating, discussing the same idea, just give you more practice. So if y here equal to c divided by square root of y, and y takes the value from 0 to 1, let's check this is the right form. Yes. Now move to find the c according to the definition. The integral from negative infinity to infinity for this p.d.f, for a p.d.f to be a p.d.f, this integral have to be 1. So this means the integral from 0 to 1 y to the power negative half dy equal 1. Why here we make it y to the power negative half? In fact, we have y 1 divided square root of y. So it means 1 divided y to the power half. If we try to put this in the numerator, so we have to transform the power here into negative 1, into negative sign. So this will be, if we try to find this integral, again it's a per function, so this will be y to the power negative half plus 1, which is half divided half, all this equal to 1, and don't forget to substitute by the limits of the integral. So this will be c. Here we are dividing by 2, so this means we multiply here by 2. So this is 2c y to the power half. And then we'll substitute from 0 to 1. As we can see here, if we substitute for y by 1, this will be 1. If we substitute by y with 0, this will be 0. So c at the end to c equal 1, then c equal half. C equal half. I wish all the problem that I discussed with you is clear for you. Here y equal half. I think I stop here for this lecture, and we'll discuss in the next lecture the cumulative distribution function. أستودعكم الله.